Hey everyone, how goes it? Welcome back to Computer Science 552 Game Development. I'm your instructor, Dr. JJ Shepard, and today we're going to continue our discussion about game design and development. In the past lectures, we focused on the concepts and roles related to the game production process. We began discussing the game design pre-production phase. Today we continue this discussion. We turn our attention back to the programmer and continue discussing elements related to the technical design document. We explore more about game programming today. In a previous lecture, we discussed some of the values and concepts related to software engineering. Creating a video game is an exercise in software engineering. Software development processes help us plan and manage the tasks required to create software. A software pattern is a general, reusable solution to commonly occurring problems within the given context in software design. Some common software pattern categories include structure patterns, behavior patterns, creator patterns, and concurrency patterns. We focus on a particular behavior pattern used frequently in game software called the game loop pattern. The game loop pattern helps us organize the game behaviors into common occurrences. Each game loop iteration progresses the game. The event step involves gathering information about occurrences that have happened since the last game loop iteration, and applying the necessary actions related to the event. User input, collision detection, message handling are common events. The update step modifies the data periodically based on the previous event and data. Moving the player, destroying an asteroid, collecting a coin are tasks commonly performed during the update step. Finally, the draw step displays the results of the update. In games, a frame is an abstract unit of time between each game loop iteration. Typically, one game loop iteration is equal to one frame, which is equal to one turn sequence iteration. Each frame progresses the game. Real-time games mean that the frame progression matches closely to actual time. Sports, real-time strategies, platformers, etc. are examples of real-time games. Turn-based games mean that the frame progresses only when a certain criteria is met. Role-playing games, chess are examples of turn-based games. As mentioned, there are steps that appear to exist outside the game loop pattern that we need to consider. The initialization event is where all the data or resources for a game are created and set to their default values. This event only occurs one time, and it is used to start the game loop. Within the game code, usually this corresponds to programming functions called start, begin, or init. In contrast, the finalization event is when the data is deallocated from memory. This also occurs one time to end the game loop. In code, this usually corresponds to programming functions called end, stop, or destroy. As both of these events only occur once, they could be considered to be outside the game loop, but in the end, they are just very special kinds of events. This concept can be used to create most games. However, if we're going to create something more advanced, then we need to consider some additional design and planning. More game features require more sophisticated software structure organization to better organize the behaviors shown in the game loop pattern. Speaking broadly, video game or just game software is the entire collection of the game-specific code, libraries, systems, and engines that compose a video game. The game software system is the code which runs or drives the game. Typically, it is foundational software that calls or invokes the game loop pattern functions that we write in the game-specific code. It contains software libraries that is used to write game-specific code. However, this is commonly considered to be separate from the game-specific code. As mentioned, it is foundational code that we build our specific game off of. A game engine provides many of the features common in most modern games. We do not need a game engine to make a game, but as a developer, it can speed up the process. We keep in mind that game-specific code is the software specifically developed to create a game. It is separate from the game software system. Most commonly, it uses provided features and programming interfaces provided by the game system. A game engine is a software framework that is used for developing games, and it includes necessary software libraries and programming support. The engine contains graphics libraries, physics engines, input managers, audio managers, message passing, and etc. As mentioned, a game engine is not required for making games, but it may speed up the development time. In most cases, the game engine can be considered the same as the game software system. They both contain the necessary software libraries to create a game. They both are in charge of executing the game loop pattern. Some non-typical or non-trivial games may require the use of additional engines that exist outside the context of one single game engine. We keep in mind that the game software system is a broader concept and game engines are a narrower implementation of that. Understanding this, today we begin discussing game software structures and how they work. Game software structure can be viewed in a slightly different way than most object-oriented designing software. The Entity Component System, ECS, puts more stress on composition over inheritance. It focuses on not what it is, but what it does. We also keep in mind that composition was another version of association or the has-a relationship. This relates heavily to the concepts of the observer pattern or mediator pattern. The component allows for a single thing or behavior to span multiple domains without requiring specific relationships to each other. This is considered a decoupling pattern, and in many ways it is common with the composite pattern. This is where programming objects are composed of other programming objects. Component-based development emphasizes the separation of specific functionality with respect to a wide-ranging functionality available throughout a given software system. Components for games are classes of behaviors. We create classes of behaviors instead of classes of things. This is opposed to hard-coding functions or methods within one large monolithic class, meaning writing everything in one programming file or writing all the code in just a main method. The code for the components are based on the game loop pattern. Separate functions for events, update, and draw are expected. And typically within a game engine there is a component programming interface for which all components implement the game loop pattern. Game objects are the abstract nouns in a game. Every thing in a game is a game object. Every object, player, every enemy, every rock is a game object. In relation to the entity component design, they are simple containers for components, and in many cases, game objects can be considered to be components themselves. Generally, classes are not specifically created for different game objects. There is no class written for player, a different class for enemy, and a different class for exploding ball, or a different class for a heads-up display. Game engines commonly have one universal game object data type, which is not intended to be extended via programming inheritance, but instead just act as a simple container for the components and some additional metadata. Game objects are differentiated based only by what behaviors they perform. The difference is not in the data type, but rather how it behaves. By using this structure, it allows for functionality to be abstracted. Many game objects perform the same actions, so they may share the same components. We can see that both player and enemy move and draw. We can consider writing one class move and another class draw and simply add those to the player and the enemy game objects. The component's attributes may be different in each instance, but the component does the same action. A player's speed and an enemy's speed may be different, but they still move in a similar way. From a functional standpoint, they do the same actions, just with different values. Game objects may swap in and out different behaviors. The flexibility of being able to decouple can allow some game objects to either gain or lose abilities. Writing game code requires understanding what are the nouns, the things, and what are the verbs, the actions or behaviors in the game. One way we could do this is by noticing the nouns and the verbs when you're reading the game design document. By categorizing the nouns and the verb, this assists in writing the technical design document. Game code is generally composed of game objects, the nouns or things, and components, the verbs or actions. This becomes the foundational structure of games. We always keep in mind that communication is fundamental to all parts of this, and as programmers, we are learning how to speak to the machines using programming languages. By identifying nouns and the verbs, we may speak more clearly to the machines in the same way that we speak to people. When we are designing games, it may be useful to draw out the concepts so that ourselves and especially others may understand how to create the game. In software engineering, we are aware of the Unified Markup Language or UML diagrams which help us design software. A component diagram is another UML diagram which demonstrates how components are connected, forming a larger system. It is very similar to a UML class diagram. It's a specialized version demonstrating the provided and required programming interfaces. Components are typically drawn with a box with an identifier. The phrase component is also typically placed in this box as well. It may also have an icon composed of a larger rectangle with two smaller rectangles centered around one of its edges. Component diagrams can be created in a variety of ways. Components connect to each other using programming interfaces. We always keep in mind that programming interfaces are not the same as user interfaces. These instead create the rules for other programmers by establishing the expected functions or operations to be implemented or written. Through these connections, the components communicate with each other. One way to model this is by using a ball and socket connector. The ball represents what the component provides, information or functional wise. The socket represents what the component requires, again, information or functionality. Above context can be provided over the symbol to better describe the relationship. This helps us better understand what it is needed and what is provided. Component diagrams can be created in a variety of ways as mentioned before. These relationships can be drawn from component to component or from game object to component. Game objects require specific behaviors to be provided. This kind of diagram can get very messy very quickly, as game objects are more of a container in concept. We may consider designing it more in this way. We can understand that components may be composed of other components. As mentioned before, game objects are components which are composed of other components. These internal components can be demonstrated by enclosing them inside of a larger one. With large systems like games, this creates a better understanding of how the action can be grouped into the structures. For a game code design, it is useful to further differentiate between a game object and the component. We can use GO to represent the game object and component to represent the behaviors. Using this, we can establish what game objects need to do by enclosing them within the game object structure. The internal components are then connected together to create the game object. Typically, we focus on implementing the game code through the components and their provided programming interfaces. The game objects and their components are smaller parts of an overall game system. In game design, we discuss how all games are systems. Commonly, the game system is the code which runs or drives the game. It is in charge of calling the functions that relate to the game loop pattern. These functions can be considered event messages that are sent to each game object, then delegated to each component. We notice a new kind of connection between the ball connectors. This is a slightly different kind of relationship that is not as strong as the connection between the ball and the socket. In that type of relationship, the socket implies a very strong dependent relationship that must be provided by another component. However, between the ball connectors, the relationship means that the dependency is not quite as strong. This is also why we denote this relationship using a dashed line instead of a solid one. This may seem like a strange kind of relationship to have, but consider that these types of connections relate heavily to the concept of event messages. We just learned that these are broadcast from a source, acquired by a receiver, and then delegated to the related components. We considered that the source provides the message, and the components provide receivers that listen for the messages. As this kind of system focuses primarily on broadcasting messages to corresponding components, we know this is based on the concept of the observer software pattern. This software pattern creates a one-to-many dependency, so that when the state of one object changes, the dependent objects are then notified. This is great as one message may be delegated to any number of components. So for instance, init event, update, draw, and final can all be broadcast from the game system to each game object. Then, each game object delegates those messages to each component to handle the steps separately and differently. This implements the game loop pattern. In addition to the game loop pattern, the game software system also is composed of libraries, other systems, and programming interfaces. This provides the game developer with features commonly found in games, such as user input interfaces, physics systems, and other useful software libraries. Game software system can be the game engine in most cases. As we've mentioned, the dashed line represents delegation of the required action to be provided by the functions within the component. Delegation meaning entrusting a responsibility, or for our purposes, delivering an event message. This is an event message that is broadcast to all the components within a game object. One event may have code handling it in several different components. The components handling these events can be considered listening for those messages. The delegation is used so that one event message may be handled by any number of components. The same event may be handled differently by many different components. Getting hit by an enemy's attack both will reduce health and knock the player backwards. This one collision event will be handled by both the health system and a moving component. A larger example of this is update may be different from component to component, but they all still must update each frame. Consider in a 3D game the first-person move component that is going to be used differently than a look around component. They are two different actions that both require updating. Both update something different about the game. As mentioned a few times, component diagrams can be created in a variety of ways. As we may also consider that the ball and connectors from the game system could in fact be considered to be a socket connector. However, the purpose of creating diagrams is not for the sake of creating diagrams. It is for the sake of communicating an idea for others to understand and implement it. It is simply a recipe which can be written in many different ways. As components commonly implement programming interfaces, these functions are assumed to be written in the component's code. As mentioned, the programming interface for a game component typically has functions representing each part of the game loop pattern. Commonly, these are called events, update, and draw. We also see some more specific events such as init and final usually in there as well. Keeping all of the common messages in the diagram can make for messy designs, so there are some assumptions that are made for the sake of cleaner diagrams. The game system is composed of collections of components called game objects. Game objects are composed of behaviors called components. To make it cleaner, we place the structure within the other structure. The game system follows the game loop pattern, meaning it handles the events for each game object and for each component within. It then updates each game object for each component within. Afterwards, it draws each game object and for which each component within, and continues looping. With this in mind, we typically omit drawing the game software system's events and our structural diagrams. It is my academic duty to explain the classic ways to represent an entity component system and all the concepts related to its designs. However, speaking bluntly, we are making games and not just diagrams about making games. In my professional opinion, these structure diagrams can be further simplified without any loss of detail. First, we can remove the need for sockets and joints and just have simple associative arrows between components that show these specific events. This can be both related to a specific event message that is sent from one component or another, or required data access where one component requires the information from another. While the usage is slightly different, we can see the use of one kind of arrow, a solid arrow, demonstrating the dependencies and the relationships. When creating a technical design document, it is important to have details regarding the game object and components. For each game object, it can be useful to provide the name or the identifier of the game object, a description, a brief summary of what the game object is and what its roles are, required components, a list of behaviors that are assigned to the game object. There will be more details in discussing advanced structures, such as tags or categories, child and related game objects, and whether or not the game object is prefab or unique. For each component in the technical design document, we provide the critical information regarding its functionality. This includes the name of the component, a description, a brief description of what the behavior in the component provides, associated components and game objects, is a list of all of the other components and game objects that relate to this one. To keep it simple, just look for the outgoing arrow from this component to the other. Other is extra internal data and functionality that assists the component, commonly not put in the component diagram but found in the UML class diagram. We keep in mind that these are high-level descriptions of the behavior and not concerned with strict implementation of them. In other words, in this type of description, you would not go into the detail of saying something like, this variable needs to be an unsigned 32-bit float. No. We leave that up to the programmer implementing or writing the software to interpret this from the notes provided. We take information from the technical design document and start writing or implementing the components. The designs in the technical design document are not overly detailed and leaves interpretation up to the programmers. With our knowledge of the structure and behavior of the components, we can now move more thoughtfully and write the code. With this knowledge and our development experiences, we can understand components only need to implement functions specific to its purpose. Not every function needs to be overridden. When writing the code, we consider each of the steps of the game loop and then address the events. What messages are we listening for? Update. How does the data change? Draw. How do we display the change? Components may only need to implement one of these common game loop functions. For the technical design document, game object and component diagrams are preferred over other types of structure diagrams. Know that there are many kinds of diagrams used in software engineering. Creating a component diagram then demonstrates how to put it together, while also leaving some interpretation to the programmers. Alternatively, creating a UML class diagram shows how the code is constructed. We're not going to go over creating a UML class diagram, as more often than not, it doesn't serve a very useful function when we are developing a game. Now we're going to take a look at the structure by using a previously developed game concept. We're once again going to use the high-low game, but this time examine how it is structured. Reviewing this game again. About. High-low is a classic puzzle game where the player must guess the correct value randomly picked in only a few guesses. Materials include a player and a referee. The setup. The referee selects a secret random value from a known range of values. For this example, we're going to assume the range is from 1 to 100. The referee knows that the player only has a fixed number of guesses. For this example, we're going to assume that the maximum count is 3. The referee then sets the player's guess count to 0. Turn sequence. Step 1. The referee informs the player that they have selected a secret number from the number range and they only have a few chances to guess it correctly. Step 2. The player then guesses a value. Step 3. The referee compares the player's guess value to the secret number. Step 4. The referee increases the guess count by 1 and checks it versus the maximum guess count. Step 5. The referee then tells the player if their guess was higher, lower, or equal to the secret number. Step 6. If the player's guess was equal to the secret number, then the referee informs the player that they have won the game. Step 7. Otherwise, if the player either guessed higher or lower and is still below the guess count, then they will inform the player and repeat from Step 2. Step 8. If the guess count exceeds the maximum number of guesses, then the referee informs the player that they have lost, tells the player the secret number, and then ends the game. The player wins when they guess the secret value within a fixed number of tries and loses otherwise. First, we can immediately identify the game objects as they were listed in the materials section. Both the player and the referee are the only 2 game objects in our system. This is a good time to note that a referee acts as a game's official. This game manager may appear in many different forms in the future, but the concept is still the same. We can now start seeing the components as the actions related to the game. First, we see within Setup that there are behaviors required to occur during the initialization event. We keep in mind that this structure is following the game loop pattern for behavior. We see this continued in the turn sequence. Each of these steps have been grouped together into the behavior that will follow these steps: events, update, and draw. Thinking about how these are grouped, we can start understanding that the main actions to be seen are picking a secret number, making a guess, checking the guess, and informing the player. When we associate the behaviors with the objects, we can then group together the game objects with their components. In our example, the referee is in charge of picking the secret number, checking the guess number, and displaying the output. We can see the referee game object contains the components pick secret number, check the guess, and show output. These all relate to the abstract behaviors that the referee is in charge of. We can see the associative connections between the components where, after picking the secret number, the referee must inform the player by showing this as an output. In a similar way, after the player's guess has been checked, the referee must once again inform the player. Both of these relate to the associative relationship between the 2 components and are defined above as the line "inform the player." Looking to the right, we notice that the player has a single component, user input. This component is then connected to the referee's check the guess component. We can assume that this is a special event, just like informing the player, that is then updated and drawn. Looking at this design, we could start seeing how we can improve and simplify what we have. We notice that the components pick secret number, check guess, and show output are all behaviors related to the secret number data. This information was randomly picked and then checked against the player's guess. More to the point, those separate behaviors relate to the game loop pattern steps, events, update, and draw. While we may keep them as separate actions, it makes more sense to group them into a single component where we organize the separate actions into the events, update, and draw steps within one component. This simplifies the overall design as now we have less components to worry about. However, there is a trade-off. More components can make the structured design more complicated, but it makes for the code more flexible by modularity. Modularity is the way the components within the system can be separated and recombined in different ways. By combining the separate behaviors into one, we reduce the code flexibility, but simplify the design and increase the performance. The other trade-off to consider is that having to pass data from one component to another takes real practical time, so if we can skip that step and transfer the data more quickly, then it increases the overall performance of our system. We must always be aware of the trade-offs of time and space and ensure that we are designing solutions appropriately and not over-designing it. This ends up being our structural design for the high-low game. It's not terribly exciting as the game did not require a complicated design. In many ways, it is more useful to see this in terms of the behavior rather than the structure. When we examine the behavior with the structure, we can start seeing how this comes together. The referee is the game object that contains the component Secret Number Manager. Within this, we see the different events, update, and draw steps within that component. This is the design that we used before, and it was featured in the referee's code. The user input component can be viewed as a flowchart as well. This one is not as complex as the referee, as it only features the operational rules of providing a guess. We can assume that these are events, and when the game starts, we are provided the input system that we need: a keyboard input, controllers, touch controllers, motion controllers. This is the component that listens for the user input. In our case, it is waiting for a number to be entered into through the command line interpreter, or the CLI. Once this event happens, then the number guessed value is passed to the referee. Creating the game object component structure and combining it with the flowchart shows the behavior of the components is a great way to communicate your ideas effectively. These details are very useful within the technical design document. This is a very simple example of a game, but understanding the structure can help us create something a little more advanced. With this in mind, we take a look at a more advanced game example. This one is very different from the last example as it is not turn-based, but it is real-time and features interactive movement. However, this can still be designed effectively using the game object component design and using the game loop pattern. Our problem is to create a game called Table Tennis for Two. We're going to assume that the full game concept has been written in a game design document wiki, which contains all the formal and dramatic elements. You can find the example of this wiki included in the course notes. From this wiki, we can derive some of the requirements. 2 players must be able to control 2 different paddles simultaneously. The players may only move their paddle up and down. A ball starts in the center of the board initially. When one of the players chooses to start the game, the ball randomly chooses a direction and a fixed speed and starts moving. The ball must be able to bounce off the player's paddles and off the boundaries on the screen. When the ball bounces off the walls, it must reflect 90 degrees from the incoming direction. When the ball bounces off the player's paddle, its reflection angle is based on the center point of the ball and the collision point. When a ball collides on either of the player's goals, then the other player scores a point and the game resets for the next round. A referee keeps track of the score, and the first player to receive 10 points wins the game. We can start seeing the game objects when observing the nouns in the requirements. We see 2 players, a ball, and environment being the walls and the goal, and finally the game official or manager called the referee. We can start seeing the components by noticing the verbs. Focusing on what is related to the player first, we notice that some of these can be related to very simple concepts. User input is needed to access the controls and apply them to the paddle. Position, rotation, and scale is considered to be a special kind of component called the transformation. We will go into a lot more detail about the importance of this component in future lectures. We can also assume that there needs to be collision detection, which is typically handled by a component called a collider. For now, we'll just assume that this is a simple geometry like a circle or a box that will detect collisions with another collider. We can see one way to draw the component diagram is showing how each GO is sharing the same components. We can also view this in a different way, which shows the interconnections between each of the components. Both ways to draw this is valid, but typically it's more useful since it shows the interconnections within the subsystems. We can see how the user input moves the player by updating the transformation component. We can also see how the collider and the sprite components need to access the location provided by the transformation component. All of these interconnect together with event messages and the data access. We also notice that the two structures are identical, and we can consider a way that we can combine the two structures into something replicatable. This is called a prefabricated or prefab game object, where it creates it once and then replicates it many times over. This is the same concept as creating a programming class that creates instances that we call objects. We can reduce the complication of a design by using only one instance and noting it as a prefab in the technical design document. We typically put this beside the GO. Now we could see the same for the ball. Here's how we can design the game object. Once again, we see the interconnections between each of the components. We notice that the collider detects the collision, but the handle the goal collisions are handled by the ball movement script. We consider the ball movement component to be listening to the colliders. When the messages are sent to the collider, it will broadcast it to any component listening and in turn will handle it. We can now see this with the referee. Notice that we have its component called the Scene Manager. This is a commonly used concept that represents the roles of the game official, otherwise known as a referee within the game. The key idea is the role enforces the constitutive and some of the operational rules of the game. We can see the referee simply diagrammed here. This is where we start putting together the other game objects and start seeing the bigger picture. Directly related to the referee are the goals. We can see here how we've created a game object, and knowing that we are going to make this into a prefab of two different goals. Regardless, the goals need to be able to detect the collision with the ball game object, and if this occurs, it sends a message event to the referee saying who scored a point. Now, we could put the rest of this together to see the overall structure. This helps demonstrate which game objects will have which components and how they will be related. However, this does not describe how the components are implemented, and this would be more appropriate for a flowchart. We should start considering using both to describe our designs. In this lecture, we've demonstrated the ideas related to the game code by introducing and demonstrating the game object and component pattern. This structure is fundamental when understanding how to create games, and will be explored throughout this course. With all that being said, get structured, and I'll speak at you next time. Now it's time for a bonus round. What is a game engine? A game engine is a software framework for developing games and includes necessary software libraries and supporting programs. What is game code, and how is it related to the game engine? Game or game-specific code is the software specifically developed to create a game. It is separate from the game engine. What is a game component? Components for games are the classes of behaviors. What is a game object? Game objects are simple containers for components. Where must we put the details and diagrams about game objects and their components? In the technical design document.